So how do we find the amount of work done by this person in pushing himself and the crate up the incline? So this problem is not that straightforward, so I'm going to provide some hints in this video to help you get through it. We see our knowns there, the mass of the person, but not the mass of the crate. We know that the applied force we're going to call F sub A is 500 newtons, and we're moving 4 meters up the inclined plane at an angle of 20 degrees. Of course, we start with a free body diagram. We're going to diagram the crate first. The applied force is the upper right. The normal force is normal to the surface. The force of friction on the crate between this surface right here. We have to have some kind of friction in this problem because without friction, this person can't get grip with their shoes and push it up the inclined plane. If it's perfectly frictionless, we couldn't get it up the incline. So there's got to be a force of friction from the crate and the force of gravity or the weight of the crate pulling down. Now, what we're going to find out is that this is not enough to solve the problem because we also have to consider the amount of work done on his body. So we're also going to need the free body diagram of the man. So let's draw another free body diagram in your solution. So for your engineering paper solution, make sure you have two free body diagrams. And as you can see, they're kind of somewhat complicated, but it's really going to simplify once you set everything up. The force of friction between the shoes and the floor, we're going to call it F sub F, whereas this one over here, it was a force of crate. See, this force is opposing motion as you go up, but right here, the friction against the floor is actually helping the person do work. So it's going up this direction. This is normal force for the person, whereas this is normal force from the crate. This is the force of gravity on the person. This is the force of gravity from the crate. Now we have to use the Newton's third law to see that for every action, F sub A, there has to be an equal and opposite reaction for F sub A on the person. So what is it that we're looking for? As you'll see right here, we're looking for the net work on this, which means we had to take the force of friction times delta x and then times the cosine. Now these two things over here are going to be pretty easy. This is going to be 4 meters like that. And this is actually going to be 0 because the force that's being applied, in this case by friction, is along the incline. See how odd of a problem this is? We're not talking about the friction here. We're talking about the person's friction with the floor. So the shoes are not only allowing him to push himself up the incline, as we can see here with the force of gravity, but also we're using an applied force right here as well. So this one helps you do both of those. Friction without friction, it just doesn't work. Oh, and it doesn't do work. All right, so all the work is done by the force of friction between the man's shoes and the floor. So in your solution, you can say that this F is going to be F sub F in this diagram. So not the force of friction in the crate, but this one over here. Now, if we do a free body diagram to find F sub F, we can find out the work then. You could try to do a free body diagram in the X and Y direction here, in the X and Y direction here, but all we're really looking for is that one right there. So why not just start with that one to see if we can get everything that we need? And sure enough, once you use Newton's second law for the man's friction, well, actually for the friction between the floor and the shoes, we do the summation of the forces in the X direction only, and only for this state's free body diagram here. And look what we get. We get an equation that allows us to calculate the force of friction if we know the applied force, which in our case is 500 newtons, and also if we know the weight of the person, which we can get right up here from the mass and the acceleration due to gravity. Now this angle right here is going to be this angle 20 degrees, which is the incline angle right there. This is equal to 0 on the right-hand side because it is moving at constant speed, as it says up here. Makes an angle, let's see. Yep, constant speed right there. So if we look very carefully at this one, let me pull this up just a little bit so you can see all of it. On this side right here, the sum of the forces in the X, just taking a closer look, we have this one up and to the right, this one down and to the left. So that's why it's minus FA. And then the component of FG along the X-axis is FG times the sine of 20 degrees. So that's what goes there. So if you solve for this, you can get a number and then you just plug it right in here. And then we know that the force of friction is along the same direction as the delta x. So this right here is going to be 0. So that gives you cosine of 0, which is 1, 4 meters right there. And you'll have a value for this based on one application of Newton's second law. So we could have had 4 different equations and gotten really messy, but what you do is you set up your free body diagram and then you target your unknown and then simplify which equation is necessary of the 4 Newton's second law equations from those 2 free body diagrams. That's a mouthful. And so this is a difficult question because of this last part here. If we just said how much work is done by on the crate, if we just said that and stopped, easy problem. 500 newtons times 4 meters and you're done. But because we have to do the work from the person as well, it's going to be more than that in this case. So if we took the 500 and multiplied it by the 4 here, we would get 2,000 Newton meters, which is 2,000 joules, or 2 kilojoules. So that would be just this part right here. But we also have to consider that part. So your answer should be greater than 2 kilojoules because they have to pull themselves up the inclined plane as well. Normally in a problem, you're not interested in so much the work they do on themselves, but since that's a factor in getting you tired, it does actually play into how much work you're doing in this case. All right, hope these hints help. We'll see you soon.